here is a little bit of a video going over those last couple slides from last class. So hopefully you've looked over the question. It was in the outline, but we're basically going to start with this idea of ethane dioic acid. It's a diprotic acid, so we know that it's got two H's. There's one, there's two. What's kind of crazy is that it also is hydrated. So just like the magnesium sulfate that we played with the Epsom salt, and we talked about how water will stick to it, water is also sticking to this acid. So what's being done in this investigation is trying to figure out how much water is stuck to the acid by titrating it with some sodium hydroxide. The sodium hydroxide will only react with the acid, not with the water, so we can kind of figure out moles and grams and molar masses, and then we can figure out what that X is going to be. So that's the plan for this investigation. So we have a mass here. We're not going to use that until the very end of the investigation, but do remember that we've got this at the very end. This mass is dissolved in water, and it makes up this volume. And then we take a small sample. We use the word aliquot. We're going to aliquot out a little sample of that. So this is our total, but we're going to take samples of the total to run our titration. We're using phenolphthalein so that we can see that pink change. And now, finally, we can talk about our data. So the initial burette reading, remember that burettes are kind of weird. They read from 0 when they're full, and then it's like 1, 2, 3, and it goes on down. So we can measure the amount that was released by reading the quantity on a graduated cylinder. So if I started at 0 and I went down to 13 to measure the volume in this titration, trial number 1, I'm just going to subtract. 13 minus 0 is 13 milliliters cubic centimeters of the sodium hydroxide. Sodium hydroxide was released from the burette to neutralize that first 25 cubic centimeters of the ethane dioic acid. So instead of refilling back to 0, titration number 2 started at that 13 where we left off here, and more sodium hydroxide was released until we got to 25.70 milliliters. To figure out how much we released, we're going to subtract 12.70 cubic centimeters. Same thing here, subtract cubic centimeters. Uncertainty of the volume of sodium hydroxide added in cubic centimeters. The uncertainty is going to be the sum of these two guys, because I was subtracting to find the volume added. Because I subtracted to find the volume added, I'm going to add the uncertainties of the two measurements that I subtracted. So the uncertainty of my volume of sodium hydroxide, is going to be 0.05 plus 0.05, which is going to be plus or minus 0.10 cubic centimeters. That's our uncertainty. So now we're going to calculate the average volume of sodium hydroxide added in cubic centimeters in only titrations 2 and 3. Remember we talked about in class how we throw out titration number 1. This is our, that's what's close. I knew that I needed to really slow down when I got close to 13. Notice that these two guys are a little bit less than 13 because I need to slow down so I didn't overshoot like I did in that first trial. So we're going to figure out first the average in cubic centimeters, and then we're going to turn our cubic centimeters into moles of sodium hydroxide. Average is pretty easy. I've got 12.70 and 12.50. 12.70 and 12.50 divided by 2 is going to give us 12.60 cubic centimeters. So there's our average volume in cubic centimeters. Now what we're going to do is calculate that in moles. So I know that my sodium hydroxide is 0.100 moles per cubic decimeter. So if I take my 12.60 cubic centimeters that I just figured out, and I turn those into cubic decimeters, I know that there's 1,000 cubic centimeters and 1 cubic decimeter. Centimeters cancels out. Now I have 0.01260 cubic decimeters. Divide by 1,000, move our decimal place 1. Oopsie. 1, 2, 3.01260 cubic decimeters. If I multiply that by the concentration that we're given, 0.100 moles per cubic decimeters, 0.100 moles cubic decimeters to the minus 3, what happens is this magic. Our positive dm3 and our negative dm3, dm to the positive 3, dm to the minus 3, they cancel each other out. Just like 2 to the second power times 2 to the negative 2 power. This is 1/4. They cancel each other out. We got 1. Same thing happens here. That positive 3 and that negative 3 cancel each other out. We're left with moles, which is beautiful because that's exactly what my question is asking us to find. So now all I have to do is multiply. This is actually pretty easy multiplication. I can do it in my head by multiplying by a 10.1. I just need to move my decimal place over 1 more to the left. Whoa, 1 more to the left. So my answer is going to be 0.001260 moles of sodium hydroxide. 0.001260 moles. So that's my answer in moles. Hold on to that for the next screen. 0.001260 moles. I'm going to jot that up here. 0.001260 moles of sodium hydroxide. That's what we just found in the last part of the question. So now I need to figure out the amount in moles of ethane dioic acid that reacted with that average volume of sodium hydroxide. I have the moles from that average volume. I just found that in the last part of the question. So if I need to figure out the moles of this that reacted with the moles of that, all I need to use are my beautiful balanced equation mole ratios. So if I had 0.001260 moles of sodium hydroxide, and I want to flip that into ethane dioic acid, all I'm going to do is put my sodium hydroxide from the balanced equation on the bottom so that I get my sodium hydroxide to cancel out. I'm going to put my ethane dioic acid on the top because that's what I want to find. There's an invisible 1 there. HOOC-COOH. My sodium hydroxide top and bottom cancels out. What we're left with is this. 0.001260 moles times 1 divided by 2 of that ethane dioic acid. So I'm going to do, if I can get my calculator turned on, 0.001260 times 1 divided by 2 is going to give us, I've got a number in scientific notation. I'm going to go with it, 6.3. I want to keep 4 sig figs. 1, 2, 3, 4. 1, 2, 3, 4 times 10 to the minus 4 moles of HOOC-COOH. So that's my answer for this part of the question. Now I want to figure out the amount of moles in that whole original solution. I'm going to go back a couple slides. Oopsie, not that many slides. So I made 250 total. But then I sampled per 25. I made 250 total, and then I titrated with samples that were only 25 big. This is a 10th of this, which means this number that I just found is a 10th of what's in that original solution. One more time. So my total volume that I started with was this 250. I took out 250. I took out from my 250, I took out 25. 1/10 of the total volume. And I used that in the titration. And I knew from the titration that I had that many moles of sodium hydroxide in the 25 cubic centimeters. And so I have this many moles of ethane dioic acid in the 25 cubic centimeters. So if I have this much in 25, a tenth of my original, to figure out how much I have in that original solution, all 250, I'm just going to multiply that by 10. So for this part of the question, the amount in moles of everything in that original solution, I'm going to take my 6.300 times 10 to the minus 4th moles. This was in 25 cubic centimeters. I'm going to multiply by 10. 25 times 10 is 250. So now I know how many moles I'm going to have in that 250. This times 10, I'm just going to move my decimal to the right, which means that this is going to turn into a -3 instead of a -4. If that isn't happy in your brain, you can go ahead and use your calculator, multiply by 10, and you're going to get 6.300 times 10 to the -3 moles of ethane dioic acid. If you don't like scientific notation, we can turn this back into a decimal. We're going to move that decimal place backwards 3 times. 123.00630 moles of ethane dioic acid. So this is my answer for this part of the question. Now I need to figure out the molar mass of the hydrated ethane dioic acid. Molar mass. Remember that molar mass is grams per mole. Molar mass is grams per mole. So if I go back, I'm finally going to use these grams that were given to us in the beginning of the question. 0.795. So my grams are going to be 0.795. My moles, I just found out in this part of the question. So that 0.006300 moles. 0.006300 moles. So again, for part, should be a Roman numeral, well, little 3. So for part 3 of this question, molar mass is always grams over moles. Grams is 0.795 grams divided by my number of moles, 0.00630 moles. Grams per moles, molar mass. Do that division, 0.795 divided by 0.00630 gives me 126.2 grams per mole is my molar mass of the hydrated ethane dioic acid. So now I need to figure out X, this. How am I going to do that? I've got the molar mass of the hydrated. Could I figure out the molar mass of the dehydrated and then subtract to find the water? Why, yes. Yes, I can. How can I figure out the molar mass of this, though? I'm just going to use my handy-dandy periodic table. So, HOOC-COOH is going to be 1.01 for this hydrogen times 2 for that hydrogen. Plus, I've got 2 carbons, 2 times 12. Plus, I've got 1, 2, 3, 4 oxygens, 4 times 16. I'm going to add that up on my calculator, 1.01 times 2, plus 2 times 12, plus 4 times 16 gives us 90.02 grams per mole. But my hydrated molar mass was 126.2, but my HOOC-COOH mass is only 90. 126 and 90. Where did the difference come from? Yes, it came from the water. So I'm going to subtract. If I do 126.2 minus 90.02, I'm going to get 36.18 With my sig figs, we always round to the smaller of the, no, sorry, we round to the largest last decimal place. Basically the smaller number of decimal places. 10th place, we're going to round this to the 10th place. So it's about 36.2 grams coming from the water. So if I take that 36.2 grams, and I know that the molar mass of water is 2 hydrogens, 1.01 times 2 plus an oxygen 16, that's 18.02 grams per mole for water. This is the molar mass of water. 36.2 divided by 18.02 is going to give us 2 moles of water. So that means that X that I scribbled all over, you can barely see it, this X here, I just made it so much worse, is 2. So if we go back a slide, up here we said that we have this ethane dioic acid. It's stuck to some water. We don't know how much water it's stuck to. Now we know. It's stuck to 2 waters. So that formula is going to be HOOC-COOH dot 2 H2Os. 2 molecules of water stuck to each molecule of ethane dioic acid. Hopefully that made some sense. More practice coming soon.